line through these 2 points is denoted by L1. Find a vector equation. So we've got the origin and we've got a line here. We know that A is on the line. So that's my position vector, OA. And then B is also on the line. So if I want the vector equation of the line, I need to get onto the line somehow. I can do that by going to A or B. Let's go with A. So 8 minus 7 minus 2. And then I need to go along along AB, and it's like by some amount. So if I wanted to get to here, for example, yeah, it'd be some multiple of AB. If I wanted to get to here, it'd be some other multiple of AB, which is where the scalar factor comes in. And I just need to times through by AB. AB is going to be minus OA plus OB, or OB minus OA. So that will be 11 minus 9, 0, minus 8 minus 7 minus 2, which gives me 3 minus 2, 2. You know what? I'm just going to erase that and write it in here. So this is the vector equation of L1. Just to say again, we could instead have used OB here, and you could have this the opposite sign because it would just be BA. You just get a different multiple here. You could also times it by something. So there's more than one answer to this question. We're then told, oh, we're asked to determine whether that point lies on L1. So I'm just going to check what the value of mu is when x is 26. So when x equals 26, remember r is x, y, z. 26 is going to equal 8 plus 3 mu. So the mu would equal 26 minus 8, 18, divided by 3, 6. And then when mu is equal to 6, r is going to equal 8 minus 7 minus 2 plus 18 minus 12, 12, which gives 26 minus 19 and 10. So the 26 and the minus 19 work, but the 10 doesn't. 26 minus 19, 10 lies on L1. 26 minus 19 minus 14 does not. Now for the trickiest part of the question. A and B, fairly standard once you've practiced them. C is your sort of curveball. We're told that the line L2 passes through the origin and intersects L1 at the point C, and that they are perpendicular lines. So I've got my line L1 that I'm going to get onto at A, like here, for example. I know I'm drawing a slightly different diagram to the first time, and then we've also got it at B. I'll leave that one out. But then we've also got L2, which passes through, let me try again, passes through the origin. And I've made it so you can see there's a right angle and that they intersect there. So this is point C. By using the fact that C lies on L1, find a vector equation for L2. Let's just remind ourselves, L1 had R equals, what was it? It was 8 minus 7 minus 2 plus mu times 3 minus 2, 2. Let me just double check that. That was up here. So what we can say about L2 is that it's going to be some multiple of a direction vector, which we don't know what it is. So I'm just going to call it A, B, and C. Now we do know that they are perpendicular. And so what that means is that the direction vectors are perpendicular. And I can say, so since perpendicular, then 3 minus 2, 2, dotted with A, B, C is going to equal 0. So therefore 3A minus 2B plus 2C equals 0. We've got a relationship between A, B, and C from that. Now let's think about OC, that precise place where they meet. So what we'll have then is that 8 minus 7 minus 2 plus some value of mu times 3 minus 2, 2 is going to equal lambda A, B, C. Now I haven't actually decided this direction vector yet, so what I can do is choose it in such a way that lambda is equal to 1. Because imagine, like, whatever I get, I can just times it by lambda to create the whole thing. I just don't need it there. So let's lambda equal 1. If that makes sense, I can just basically then get rid of it. And it's like, so if ABC was equal to, like if lambda is equal to 2 and ABC was 1, 1, 1, I could just say, I could just change it and make it 2, 2, 2 in here. And that's great because now I can link, I can write some equations down for A. So I've got, for all of them actually, sorry, I've got 8 plus 3 mu is equal to A, minus 7 minus 2 mu is equal to B, and minus 2 plus 2 mu is equal to C. I just want to make sure you're happy that I just got rid of that lambda. So remember, ABC is just a direction vector, so I can times it by whatever I want, and I've just decided to scale it in such a way that lambda is equal to 1 at where C is. Okay, there's nothing stopping me doing that. Right, that's my last explanation of it. So now I can, I've got this, but I've also got this, and I can sub in to get an equation just in terms of mu. So combine. Therefore, I'm going to get 3 times 8 plus 3 mu minus 2 times minus 7 minus 2 mu plus 2 times minus 2 plus 2 mu equal to 0. So 24 plus 9 mu plus 14 plus 4 mu minus 4 plus 4 mu is equal to 0. And that gives me 17 mu plus 34 is equal to 0. So this is minus 34. Therefore, mu is equal to minus 2. Yeah, I think that's quite awkward. I think that's potentially the hardest question in the paper because you get all these questions that you've seen before, matrices and complex numbers and stuff, okay, slight variations, but this is quite different. The fact that you've got this line, we know the perpendicular, we know they intersect at a point, and you can figure out the equation because it goes through the origin. So now I can work out A. It's going to be 8 minus 6, going to be 2. B ends up being minus 3. And C is equal to minus 6. So therefore, L2, R is equal to, I'm bringing mu back in now. It was only when at the point C when it was equal to 1. So it's going to be mu times 2 minus 3 minus 6. And finally, we're asked to hence find the shortest distance from O to L1. Now, when you have a line and you want to find the shortest distance from a point, it is actually the perpendicular. So the shortest distance from O to L1 is precisely OC. When we worked that out, we said that it was just ABC. So OC for the shortest distance is going to be 2 minus 3 minus 6. Let me just say again, so shortest distance itself is OC without the vector, and then I've written the vector down. So now we can use Pythagoras' theorem. It's going to be 2 squared plus minus 3 squared plus 6 squared, 13 plus 39, sorry, square rooted. That's the square root of 49, and hence the shortest distance is 7. Well done on your efforts here.